Okay, welcome to the lesson on intersection of three planes. I will probably be breaking this into two parts. So this is the first part. The intersection of three planes in Cartesian form, given here, the intersection is related to the solution of that system. And we've been practicing solving these systems. So depending on the type of solution you have different geometry. And, that's basically what it comes down to. We can solve it using substitution or elimination or a matrix method, whatever method. Um, and there are four geometries that have solutions and four geometries that do not have solutions. And rather than memorizing them, you should deal with them from a basis of understanding. So you have to become familiar with them. For intersections, we can have a single point of intersection, or we could have an infinite points of intersection. There's one geometry for a single point of intersection and three geometries that have infinite number of points of intersection. So let's begin with the first case. Students have a hard time visualizing this. Whatever room you're in, look at the wall in front of you, then look down at where that wall meets the floor, and then go along the left, if there isn't furniture in the way, to the corner of where the left-hand wall, the wall in front of you, and the floor meet. That is, in essence, the intersection of three planes. And that corner, not the wall meets wall corner, a vertical line, which is like an axis, but the bottom corner where those two walls meet, the floor, is a point of intersection. Okay? And of course, the walls don't have to be 90 degrees to each other for that to happen, but that's the idea. Now, one of the key characteristics about the normals of the three planes when you have a point of intersection is that the normals are not coplanar. And you can do the triple scalar product. You cross two of the vectors and dot it with the third to verify that. But that isn't foolproof, as we see. When you go to solve the system, you'll only get one solution. You'll get a unique point. Okay. So here's our first example. Start off by eliminating x. And so copy that down if you haven't yet. Well, I guess you got the notes printed out, perhaps. So we're going to eliminate x. And I'd like you to do it so you can check your work the way I'm showing here. So take 3 of equation 1's and then add equation 3. And I saw that if I added all 3, I would eliminate x. So we're eliminating x 2 ways. So go ahead and do that. Unpause the video when you're ready. When I did that, I've got this, and then I'm going to eliminate the z. I decided to go for z. So I'm taking the fourth equation and adding 4 times the fifth equation. That way the z's cancel. Pause the video if you need to. And y is equal to 1. Now I'm going to back substitute into equation 5. And when you do that, you'll get a z value. Z is equal to 4. And then back substituting even further into equation 1, you get that x is equal to 2. And so now we have an x, y, z coordinate that is the point of intersection. So by stating this, we're saying there's one answer, and we're stating the geometry, which is point of intersection. The only other thing I'd like you to do is check the triple scalar. I'd like you to do normal 2 cross normal 3 dotted with normal 1 and verify that they are not coplanar, so they're not going to be equal to 0. When you're ready, just roll the video. So the cross product and then dotting it, we get 11. The vectors are not coplanar. So just recognizing what they told us in the note is in fact true in this case. Okay, point of intersection, 3 planes intersect at a point, giving a single POI. The second case, infinite number of solutions, where the intersection is a line. And if you take a small book or exercise booklet and you open the pages, each page could be considered a plane. And the spine of the booklet, where the pages are folded, if you like, becomes the line of intersection. So that's this case. The second case, there's infinite number of points of intersection along a line. And the vectors, the triple scalar of the normals is 0, which means the normals are coplanar. Okay, so even for the example with all those pages in an exercise booklet, the normals for all those pages would all be coplanar. All right, so the example. Let's go ahead and eliminate y in this case. I saw the different signs, so I decided to eliminate y. Go ahead and start rolling through it, and then pause the video, give it a go, and then roll the video when you're ready. Okay, I get that. And I noticed something about the proportions and the numbers, the coefficients and the constants here. These two equations are actually exactly the same. You can verify that because once I've reduced or divided out, common factored out if you like, a 4 and a 7, depending on which equation, and I subtract them, I get infinite solutions. Now, the simplest way to go ahead and find out what the solution is, so we need an equation describing the points of intersection. The simplest way to do that is to let one variable equal t. So I chose z, and then I rearranged equation 4 and solved for x. So that gives me 2 out of the 3 parametrics already. Okay, z is equal to t. And then using equation 4, x is equal to 1 minus 4t. And then I can sub that into equation 1, and I get an equation for y. Okay, and just restating it, I have the 3 parametrics, and then I also wrote the equation for a line in vector form. So the geometry here, oh yes, we're going to do that next, but I didn't state the geometry. The geometry is what? Well, it's not a point of intersection. Three planes, non-parallel. We'll get into that a little bit more. Intersecting at a line. Okay. All right, here's the triple scalar. And you can see that it's 0, verifying that the normals are coplanar. Third case, it's actually the cases get simpler as you roll through these. In this case, 2 of the planes are coincident and 1 plane is not. And so it really becomes the intersection of 2 planes, which we had in 9.3. Because 2 of the planes are coincident, the intersection is a line. And the line of intersection, of course, is in the direction perpendicular to both normals. Okay. The 2 planes are coincident, and the third plane is not parallel. Okay. All right. Solve the following system of equations. Okay. Do you look for it? Which of the planes are coincident? Plane 2 and plane 3 are coincident. How do we know? Well, normal 2 times 2 is equal to normal 3. And 2 times the constant in 2 is equal to the constant in 3. Okay? So we're going to have a line of intersection. Okay? A line of intersection. And to find that, we just have to solve 2 of the equations. All right, so I'm going to work over to the right here. I'm going to use equation 1 and 2. And I'm just going to eliminate z, I guess. I'm going to add 1 and 2 together. I get 2x minus y is equal to 6. I need the equation for that line, so I'm going to let x equal t. I could have let y, but then I have to divide by 2 and end up with fractions. So when I let x equal t, Then y is 2t minus 6. I still need z, so I'll sub into equation 1. Go ahead and pause the video and, go ahead and do the work. All right. So we substitute into 1. We have t plus 2t minus 6 minus z is equal to 2. So z is equal to negative 8 plus 3t. I'm just going to restate the other parametrics. So there's the parametric equation of the line of intersection in vector form. It doesn't ask us this, but I actually sort of prefer vector form a lot of times because it's just so much more compact, I guess. There we go. We have to state the geometry. We have two coincident planes. Intersecting a third plane in a line or at a line. Okay, so a line of intersection. Fourth case, 3 coincident planes. Any of the 3 equations actually give you the complete set of points that intersect because all 3 planes are the same. Okay. The coefficients of x, y, and z are proportional, and so is the constant intersections of plane. So just looking at this, 4 normal ones are equal to 2 normal twos. I didn't number these yet, so I'm going to. Is equal to negative of normal 3. Okay, just looking at that. So the question is 4 of D1s equal to 2 D2s equal to the negative of D3? Yes and yes. Therefore, planes 1, plane 2, and plane 3 are coincident, parallel and coincident. The 3 planes intersect at a plane, and I'm just going to state one of them, parallel, and then restate the geometry. We have parallel and coincident planes. Okay, so that's it for the part 1 video. When you're ready for the other 4 cases, roll the next one.